Up to this point in the course, whenever we've talked about the gravitational force, we've always meant the gravitational force acting on a mass at or near the surface of the Earth. What we want to do now, though, is talk about gravitational force between two point masses. The rules that govern the gravitational interaction between two point masses are given by the universal law of gravitation. So if what I have are 2 point masses, m1 and m2, so I can just think of these as particles. They're separated by a distance that I've labeled r here. Then the gravitational forces that act on these two masses has the following properties. The gravitational force is directed along the line joining the two particles. So you can see where we've drawn in the line that connects mass 1 and mass 2. And the two gravitational forces that we've drawn in, so the first one is the gravitational force on mass 1 by mass 2, the second is the gravitational force on mass 2 by mass 1, and both of them lie along the line connecting the particles. 2, the gravitational force is attractive. Mass 1 is being pulled towards mass 2 is being pulled towards mass 1. 3, the magnitude of this gravitational force is given by the following equation. So big G times mass 1 times mass 2 divided by the distance between them squared. And in this case, big G has a value of 6.67 times 10 to the negative 11th, and one unit that we can use for this is Newton meters squared per kilogram squared. So this is how two particles interact gravitationally according to the universal law of gravitation. So let's look at this equation for the magnitude of the gravitational force between two particles, and let's think a little bit more about what this equation is trying to tell us. Well, the first thing that we can recognize is that the magnitude of the gravitational force is proportional to the product of the masses, m1 times m2. We've talked all semester long about the fact that forces are interactions between two objects. This equation is simply emphasizing that gravitational forces are interactions between two masses. You need both of those masses in your equation. So an object feels a gravitational force because it has mass and is in the presence of another mass. That's the interaction between two masses. The second thing this equation is telling us is that gravitational force is proportional to 1 over the distance between these two objects squared. So what we've done with this equation is we've taken that distance that we'd initially labeled r, and now we've just added this subscript 1, 2 simply to emphasize that that r happens to be the distance between masses 1 and 2. And so here when we say that the gravitational force is proportional to 1 over r12 squared, what we're saying is that the gravitational force acting on mass 1 or mass 2 is proportional to 1 over the distance between those two masses squared. The larger you make the distance between your two objects, the weaker the magnitude of the gravitational force between them. So as an example, if we doubled the distance between 2 point masses, then the gravitational force would be reduced by a factor of 4. It would be 1/4 what it was before. This is known as an inverse square law and is the first of several that we'll see. The third thing that this equation is telling us is that the gravitational force is proportional to the product of the masses divided by the distance squared, and that constant of proportionality is big G. Because big G is such a small number, gravitational forces are in fact incredibly weak. Now, we don't typically think of gravitational forces as weak because drop anything, it falls, right? We're always in the presence of gravity. But it's the fact that the Earth is such a large mass that makes those gravitational forces significant. What we're going to see is that when we calculate out the gravitational force between point masses that have relatively small masses, we're going to get incredibly weak forces. The last detail that we want to make sure we recognize is that, of course, this equation gives us the magnitude, but the gravitational force, like any force, is a vector. So I need to think about direction. And we said that the direction is always going to be along the line connecting your masses and always attractive. So we're going to be able to use this rule that gives us the direction for the gravitational force between 2-point masses to draw those forces in, that then we can pick a coordinate system to break those force vectors up into their components. And as with any problem, the sign you end up with in your component is determined by your choice of coordinate system. In this case, where we have mass 1 and mass 2 separated by the distance r1, 2, again, there are two gravitational forces we can talk about because mass 1 is attracted to mass 2 and mass 2 is attracted to mass 1. We want to think about the gravitational force on which mass. If we want the gravitational force on mass 1, that's this vector. If we want the gravitational force on mass 2, that's this one. The second detail is that once we've picked our coordinate system, and in this case we've said positive x points to the right, then that's going to determine what the signs are in the components for each of these vectors. So because the gravitational force acting on mass 1 points to the right, its x component will be positive. Because the gravitational force acting on mass 2 points to the left, its x component will be negative. Now if we have multiple masses, then we can talk about the gravitational force on a particular mass, but now there's going to be multiple vectors, and what we need to do is add them together. So we can work problems asking for the net gravitational force on one mass in the presence of several other masses, and that's simply going to be a vector addition problem. So we'll need to figure out gravitational force due to each individual interaction. So how does mass 1 interact with mass 2? How does mass 1 interact with mass 3? And then we'll simply sum up those vectors using vector addition.